very happy to be at least virtually in Canada again after already more than a year, or maybe a year. We have closed borders, so hopefully the borders will be open at some point. And before I will start, let me say two things. First, since Kitaev model is exactly solvable, by no means I can find any other solution for the Kitaev model than Alexei Kitaev, because that's the solution. You can write it in different ways you wish, but that's just the solution. And second, let me say once again that I will be very happy to be interrupted. Actually, I will feel more alive, and that kind of I will feel if I'm going too fast, too slow, better. Okay, so please stop me at any moment. And with this, let me share the screen. So I check it should work. And let me move this a little bit here. So perhaps you were a little bit puzzled by the title of my talk, this kind of disorder square. But I will actually talk about the role of disorder and the effects of disorder in the spin liquid. And since one of the main definition of quantum spin liquid that it's never order, so that means that it's remain disorder until zero temperature, then I thought that disorder upon disorder is a good title. Okay. Okay. So before I go on, let me say that the most of the work which I'll present today was done in collaboration with my student, Ben Han Kao, who is a PhD student in the University of Minnesota. But this work was very much related to what we did all together with Johannes Knolli, Gabor Hausch, and Redrith Mersner. And there will be free references which I will give for our work. So if you want to study it in more details, then you will see the references. Okay, so first, as I said, there are two types of disorder. So there can be some extrinsic disorder and intrinsic disorder. So basically by extrinsic disorder, I call the disorder which come from outside and which is present in all real materials. And that can be all different type of randomness. It can be defects in the lattice. It can be some vacancies in the lattice. It can be some impurities in the lattice. So it can be some stacking faults. And the role of disorder is usually very important. And even if we theorists quite often try to forget about the effects of disorder, I know that at least for experimentalists, it's usually something very important to take properly into account. And basically, we have to think about effects thoroughly. So, and by intrinsic disorder, I mean something different. I mean when so first of all, I'm talking about magnetic system, and I'm talking mostly about, insulating system, not mostly, but about insulating system. And by intrinsic disorder, I mean that the system doesn't order even at zero temperature. And though it's a negative definition, this is one of the most intuitive definition of the quantum spin liquid. And one of the example of quantum spin liquid, and perhaps the one which started the whole business, was the resonance valence bond state, which Philip Anderson introduced first in the triangle lattice. And in fact, he was trying to explain the ground state of the Heisenberg model on the triangle lattice. And this solution was shown later to be a wrong one. That's not the ground state of the Heisenberg model for spin 1/2 on the triangle lattice, because we all know now that the ground state is 120 degrees magnetic ordering. But despite of this, it's open the whole field of new materials which do not order at low temperature, but moreover, their ground state cannot be written as a product of states. And basically, instead of this, this is a composition, it's a superposition of the states with the same energy. So basically with the zero energy, if you wish to think about zero temperature, of the same energy. So it's a superposition of states from the degenerate manifold of classical states. And this state cannot be written as a product. So for this, you need to have a frustrated system where such degenerate manifold can happen, and frustration, which again Anderson say that frustration is the name of the game, can come either from the lattices, and in that case we are talking about geometric frustrated systems, or it can come from interaction, and then we can have frustration of quantum spin liquid due to interaction, and that is the case of Kitaev spin liquid. And in this case, we can obtain this manifold of the states. But what else is required to realize quantum spin liquid is a strong tunneling between these states. So resonance valence bond is one of the example. And another example, and I know that people in Canada are studying it quite a lot, that's about spinized materials, and basically about quantum spinized material, where you can first have some pyrohor, either two-dimensional or three-dimensional, where you can realize the classical IS rule. So you have a manifold of states where two spins are pointing in the tetrahedron and two spins are pointing out, and there is very macroscopic, and there is a macroscopic number of such states. And then you switch on quantum fluctuations in this system, and then you can realize quantum spinized states, which in some sense is very similar to quantum spin liquid state. So, and the model I'm going to talk today, and the system I'm going to focus on today, is the Kitaev model. And once again, perhaps for you, this model is already very well known, but just in case, so this is a model which was written by Alexei Kitaev for the honeycomb lattice, where you have, each side has 3 different neighboring bonds, and the spins are interacting via Ising-like interaction on these bonds. And already, if you look to this system classically, you can see that the system is frustrated because you cannot satisfy all these interaction at the same time if you put the spins along y-axis, like to satisfy the blue bond, then the green and red bonds will not be satisfied. So it's clearly there is a frustration, and there were many, many different works which shows, even from classical perspective, how this frustration can be understood. But then Alexei Kitaev actually wrote this model to solve it exactly. So he somehow construct this model, and he did this by a particular representation of spin with the help of Majorana fermions. So each spin was represented with the 4 Majorana fermions, and all these beautiful plots from this nice review by Hide Takagi et al. Published 2 years ago. And then basically for each spin, you have 1 Majorana fermion C, which doesn't have any spin index. And then you have this Bx, By, and Bz, such that each component of spin as gamma can be represented as a bilinear product of these Majorana fermions, like B gamma C. Okay? And then with this help of these Majorana fermions, I will just say a few more words in a moment about the exact solution. He showed that this is indeed the 2-dimensional model which has exact solution, which is already quite a rare thing. And second, that it has a quantum spin liquid ground state. And this is great because people were already thinking a lot about quantum spin liquids, but since quantum spin liquids usually comes due to strong fluctuations, and therefore they appear in the strongly interacting systems, then there was no way to find the exact solution. And all our knowledge about quantum spin liquids before this model were mostly related either on some one-dimensional examples or on the mean field solution or on the pure numerics. And here, basically, we got a playground which allows us to study many phenomena. So basically what I'm going to talk today is, so first I want to introduce this Kitaev quantum spin liquid and show that Majorana fermions are emergent quasi-particles, that's fractionalized quasi-particles in the system. And I'm going to consider, so what happened with this quantum spin liquid if you put inside this spin liquid some sort of extrinsic disorder. You can put some bond randomness, or you can put vacancies or quasi-vacancies. I will also discuss the thermal disorder, because since the Kitaev spin liquid is fractionalized on Majorana fermions at Z2 fluxes, and these Z2 fluxes are static variables which are nevertheless can be excited by infinite temperature. So this Kitaev spin liquid also has some intrinsic thermal disorder coming from this flux degrees of freedom. And then what I'm going to discuss, and this is completely new work which we just put in the archive maybe 2 weeks ago, is since we have these Majorana fermions, the solution of Kitaev spin liquid is that these Majorana fermions are non-interacting quasi-particles at each flux sector. And since these Majorana fermions are non-interacting, then we can think that this gives us a very nice playground to study the localization defects, which are again due to Philip Anderson, which consider what disorder is doing for the single particle wave functions which are non-interacting. And there is the whole field about Anderson localization, which was discussed and developed in last 50 years, or maybe not, maybe more, 60, 70, I don't know, quite long time. And it was interesting to look how this idea, this concept of localization, how they can realize themselves in this new playground, which is the quantum spin liquid. And in part 2, rather briefly, I want to show how this development can be used to understand one of the Kitaev material in which disorder plays a very important role. And this is hydrogen intercalated lithium iridate. And this part 2 is based on these 2 other papers. And the answer is that bond disorder and the side disorder in form of vacancies and or quasi-vacancies, they in principle can coexist. But in order to have a very robust description of experimental key findings in this compound, it seems that vacancy play a really important role and can account for the majority of experimental observations. Okay. So very, very briefly, just to remind what is the fractionalization in the Kitaev spin liquid. It's all based, the exact solution is based on the fact that you can introduce the plaquette operator on each of the hexagons, which is the product of the spin degrees of freedom, which corresponds to these outgoing bonds, okay? So when you multiply the spins, you get this plaquette operator, and you can obtain this plaquette operator for each of the hexagon. You can show that all of them commute with the Hamiltonian. That means that you have macroscopic number of conserved quantities, and that's why the system is exactly solvable. Another important thing is that this, if you define this plaquette operator on different hexagons, these plaquette operators commute with each other on the different hexagons. And therefore, if you specify what is this WP on the whole lattice, then you can characterize all the flux sectors, and all these flux sectors will be orthogonal to each other. And it's important that this WP is a Z2 variable, so it has eigenvalues plus minus 1. So now this idea of Kitaev, so each of the components, so C spin is 1/2, I kind of move to the Pauli Matrices description. So each of these Pauli Matrices can be written as a bilinear product of these Majorana fermions, C and B. And the Hamiltonian can be rewritten in the fermionic space. One need to remember that once you go to this Majorana fermion description, then the Hilbert space in which you act is actually enhanced. And therefore, in order to perform all the calculation in the physical states, you have to implement the constraint, and you have to project all the states to the physical space. I will not go into details of that, but in principle for Kitaev model, it can be done exactly. So once you follow Kitaev and you rewrite the Hamiltonian in this Majorana fermions form, and you introduce these U variables you introduce on each of the links, and this link variable is nothing else as a product of two B Majorana fermions on the corresponding link. And then what is important that this plaquette operator I was talking before and this link operator U, they are related to each other. And basically, you can rewrite this plaquette operator in terms of these U operators and show that these link variables, they also compute with the Hamiltonian, therefore they are all also static quantities. And they also have eigenvalues plus minus 1. Okay. So now you have the Hamiltonian, which is written like this. So all these U are substituted simply with the numbers. It's plus minus 1 in different flux sectors. And in each of the flux sectors, you have a hopping Hamiltonian on the honeycomb lattice for C Majorana fermions. Then you can compare different sectors since they are all orthogonal to each other. And you can show that the ground state has all plaquette operators equal to 1. And you can choose a particular gauge configuration of these U variables. For example, you can put all these U variables equal to 1 homogeneously in all the system. And that would correspond to this physical flux sector, which is the ground state with the lowest energy. And then in this ground state, you can compute the spectrum for the C Majorana fermions. This is a trivial task now. And I will focus, so here basically is the plot from this Eugene Batome review, which is excellent review about Kitaev model. But I will be focusing in the case when the pristine model without any defects are such that all couplings are equal to each other. So it's case D. And what is important that this case D is for Majorana fermions are very similar to graphene system with where the electrons are hopping in the honeycomb lattice, and near the K and K prime points, you have these Dirac cones, this famous Dirac dispersion for graphene. And once again, in the zero flux sector, Kitaev model for Majorana fermions and graphene model are very, very similar to each other. So many analogies can be done between Kitaev physics and the graphene. Okay, so once again, quick relation between, I thought I would do it before, but relation between these plaquette operators and the U operator. So it's just the product of these U operators on the hexagon. But now we understand how we can go from the ground state where OWP is equal to 1 to other flux sector. So for this, we need to flip these U variables. So imagine that in the ground state, and we say that it's a zero flux, because you can think about this WP operator as a flux acquired by, it's like flux of 2 pi acquired by Majorana fermion when he ran around the hexagon. So in the zero flux sector, all U are plus 1, all W are plus 1. So this is the good starting point. Now, in order to create...
Sorry, could I interrupt and ask a question? So the analogy that you're making with graphene seemed to be an analogy in the band structure, the electronic band structure for graphene and for the Majorana fermions here. Is there an analogy in any physical properties as well? Anything that would be manifest in experiments?
Yes, actually, quite many of them. So when you what I'm going to discuss, for example, today about the localization effect when you put the vacancy, then that's very similar to graphene with the vacancies, for example. So what is important, the main difference comes from the fact when you go at a higher temperature where flux degrees of freedom become important. So this analogy works only as long as all flux operators are 1, okay? So once you introduce by this trick, which I'm about to discuss, and you have different flux degrees of freedom, you have another degrees of freedom, which is completely absent in the graphene. And therefore, all the properties which are connected by interplay of Majorana fermions and flux degrees of freedom, they will be quite different. So once again, that's what makes them very, very different. So the low temperature, very, very low temperature, which is below the energy of the flux gap, you can find all the similarities. And when the temperature is increasing, you start seeing how the properties start deviating from this. And another big difference comes from the fact when you introduce the time reversal symmetry breaking term. because in the way, and I will talk about this here, how we introduce it, it introduced the second neighbor hopping in the second neighbor hopping on the honeycomb lattice, but it still preserves particle hole symmetry. And this particle hole symmetry, if you introduce the second neighbor hopping, can be broken in graphene for the true electrons. And here, by the nature of the Majorana fermions, it's always preserved. So basically, there are some analogies, but there are also some significant differences.
Yeah, okay, thank you.
Okay, so basically what I want to say here is that how I can go from the ground state flux sector to all other flux sector, which will be important for me. And for this, I say, if I take one link variables and I flip u from 1 to -1, then by this I create two fluxes, because imagine that in all thin lines, u is equal to 1, and on this red line, it's -1. So it's clear that W on these two neighboring hexagons change sign from 1 to -1. Okay? And basically what is important that now by flipping these other U's, I can propagate these flux degrees of freedom through the lattice, or I can create any configuration I want starting from the ground state flux sector. Okay, so I will also need to say a few words about magnetic field. Usually in the people who are studying the exact solution of the Kitaev model, they treat the effect of magnetic field perturbatively, because in that case, you can be in this situation when you preserve exact solution. So if magnetic field is small and you have all this kind of, for example, you have a field along 1, 1, 1 direction, then you can treat this perturbation, you can do the perturbation theory, and you can obtain the effective interaction, and the effective interaction V would be nothing else. You can write it in the spin variables. That will be the free spin interaction, which in terms of Majorana fermions, okay, so here I actually forget sigma x, sigma y, sigma z. In the first term, so the first term missing sigma x, sigma y, sigma z, this product of free spin interaction. Sorry for typo. But in any case, you can take this free spin interaction and you can rewrite it in terms of the Majorana fermions. And you see that when you introduce this free spin interaction, effectively your system remains in the, so by this transformation where you apply on the ground state all these sigma operators, so your system remain in the flux free sector, in the zero flux sector. And second, you can see that basically what you introduce here, you introduce the second neighbor hopping. So that is the effect of the small magnetic field, which can be still treated exactly in this Kitaev physics. Okay, so, and what it does, once again, so here is the example which actually shows that this free spin interaction makes the model very similar to Haldane model on the honeycomb lattice with this time reversal symmetry breaking term. And basically what happens is when this kappa, this free spin interaction term is non-zero, it opens the gap for the Dirac cone. So, and this gap at this K point is proportional to the strength of the kappa. Okay? So when magnetic field is growing, kappa is growing, and this gap is also growing. And then basically this analogy with the Haldane model actually shows that the gap state is a Majorana fermion Chern insulator with a Chern number plus or minus 1, C plus or minus 1, and you have a gapped bulk spectrum and you have a gapless H modes. Once again, I will not discuss it much today, but in principle, this is the situation. Okay, so now, as I said, very low temperature, zero temperature, when we mostly have no flux degrees of freedom, is very similar to graphene. So basically, the only thing what we have by these green dots, what is shown is this Majorana fermion hopping on the honeycomb lattice. But then when the temperature is increasing and become of the order of the flux gap, the flux degrees of freedom start proliferating, and you have a state in which you can be in a different flux configuration. So slowly you will be occupying different flux configuration, and you will see that this random flux configuration, so you start occupying this flux configuration at very low temperature, and around 0.1 of the strength of Kitaev interaction, actually you are entering, roughly speaking, to the random flux sector. And then basically, if you go to the higher and higher temperature, then eventually you end up in the conventional paramagnet. So, but what is important from this figure is that there is an intermediate region for temperatures where various flux configurations are important. And of course, they will affect all these observables you are going to compute, and they will affect the spectrum of Majorana fermions, since this spectrum would be different in each of these flux sectors. And this is once again from Matonic group. So the thermodynamics, which you can study with the Monte Carlo simulation, is that you, in the specific heat, for example, you have two peaks. So the first peak corresponds to flux proliferation, and the second peak corresponds to itinerant Majorana fermion excitation. And this two peak structure in thermodynamic quantity actually shows you that spin degrees of freedom is fractionalized, and moreover, it's fractionalized very asymmetrically into two different kinds of fractionalized excitations. Okay, and then you can compute different quantities, how they are changing with the temperature. Okay, so once you are in one of these flux configuration, you understand that your translational symmetry is lost. And if you want to study the spectrum of itinerant Majorana fermions, you need to do it in the real space. And that can be done. You can rewrite this model in the real space, and you can perform the diagonalization in the real space, which can be done with the numerically with a single value decomposition. So it's on the finite size cluster. And that was already suggested by Alexei Kitaev in his original paper. So what is important that before you had this spectrum, each state of which was characterized by wave vector. Since wave vector is not anymore a good quantum number, so now instead you diagonalize your Hamiltonian, and then you have just a set of the Majorana fermions or complex fermions eigenmodes. And we're going to use it because not only in the presence of fluxes that is happening.
כן, אתה רוצה?
כן.
טוב.
Okay, so basically what I wanted to say that we will need to perform that kind of real space diagonalization also in the presence of disorder, because also in the presence of extrinsic disorder, the translational invariance is broken, and therefore we cannot perform Fourier transformation to the Fourier space. Okay. Okay, so now let me discuss this disorder in the Kitaev spin liquid, and I will consider different types of disorder. So this is the pure model. This is the thermal disorder where all the couplings are still the same, but we can have fluxes, and once again, these flux degrees of freedom is characteristic disorder in the Kitaev spin liquid. Then we will also consider various types of the bond disorder. So here it's shown in the zero flux. So some amount of bonds become either stronger or weaker, or you can have a box distribution for couplings where at each bond there is a certain probability that J deviates from one, which would be the coupling in the pristine model. And then you can introduce either vacancy or quasi-vacancy. And what I will show that in this model, what are the condition when there is a flux attached to each of the vacancies. Okay, so and the questions, as I said already, which I'm trying to answer is, since I have such a wonderful playground, can I have an Anderson localization of non-interacting Majorana fermions? Since, once again, I still have exact solution, even in the presence of disorder. So I think it's a very interesting question to answer. And another question which is very much related to the Anderson localization or to disorder effects for the single particle wave function, is the appearance of the Lifshitz tables. And you see that both of the works are quite long, and perhaps we found another playground to find this physics in the Kitaev QSL. Okay, so let me start with the bond disorder just to specify once again. So this is, once again, what the Hamiltonian is the extended Kitaev model, where in principle I can switch on or switch off my time reversal symmetry breaking term, and this is this second term. So I already said this, and once again, in reality, let me tell you that the bond disorder can arise from various reasons, and basically it can be some lattice distortion which change the exchange paths, and that's why J's are changing, or it can be inclusion of some non-magnetic sites. So basically you need something in the lattice, what is happening and what is locally modify the exchange paths and therefore modify this J. So in this case of these different kinds of bond disorder, I can characterize this spectrum of Majorana fermions by computing the density of states. So in all these plots are shown for the system size with L equal 20, so it's 2 multiplied 20 by 20, so 2L square. And the density of states is average for disorder realization, which is shown here as Jij. But also, if we consider flux degrees of freedom, if we want to consider thermal disorder, then it's also average over different distribution of these U variables, which characterize different flux configuration. So here, let's start from this plot. So dashed line shows the density of states for the pure model. So this it's shown on all the plots just to compare the situation. And you see this very large peak at E equal to 2, and that corresponds to the Van Hoff singularity of the spectrum of the Majorana fermions, okay? And also what you can see that we consider the pristine model is isotropic, and therefore the spectrum is gapless, and you see that the density of states, it grows from 0, and since you have a Dirac point, you have a vanishing density of states when omega is equal, when energy is going to 0, okay? And now we compare this pure density of states with a density of states computed for various disorder realization. So the disorder realization for the bond disorder can be characterized by two quantities. One is the density of the bonds, so how many bonds are affected by this disorder, and in this case we denote it as rho, so we consider here, if you see, 10%. And then what is this different bond? So what is this change in the coupling? And here we just consider that 10% of the bond has coupling half of the normal bonds. Okay, so normal bonds are 1. So to some extent here you are diluting the system with a weaker bond, or you can consider the system where you on this plot E, when you are diluting the system with a stronger bond, and you will see that certain characteristics are very different. So in any case, when you look, so with the blue plot shown here, the density of states computed in the zero flux configuration. So for bond disorder, we actually computed only the random flux configuration and the zero flux configuration for the following reason. The bond disorder is known to renormalize locally flux gap quite a lot, because the flux gap depends on the local coupling of the site. And therefore, when you have a big fluctuation of the couplings, you can have a very big fluctuation of the flux gap, and the flux gap can significantly decrease, or they can even vanish. So therefore, since we are not doing here the Monte Carlo, just averaging over different flux configurations, so it's more safe to consider these two extreme cases of zero and random flux. And you can see that in all these cases, so once again, box disorder means that you have this uniform distribution. So each bond is affected, and the bond box, the coupling can vary from J plus delta J 0.3 and minus, so from 0.7 to 1.3, roughly speaking. And you can see that in all these different type of bond disorder, what happens is that the states from the Van Hoff singularity are taken out, and you have a more homogeneous distribution. So you basically have either increase of the states at a higher energy end if you are doping with a stronger bond, or you start seeing that some weight is transferred to the lower energy if you have more low energy bonds. But in all this different realization of bond disorder, you see that the sharp features, kind of as a Van Hoff singularities or sharp band age, disappears, okay? So you can also see what happens if you have no extrinsic disorder, but just thermal disorder. So if you consider, so this plot here shows the situation when the randomness is coming from different random flux configuration. And what you see by this orange is that actually you have a flattening of the density of states in the whole bandwidth, and you have no reasonably strong features. So density of states is not enough to characterize the localization of the states. We need another quantity. It only tells us what is the different distribution of the states in the energy spectrum. So in order to characterize the localized nature of the states, we can use the inverse participation ratio, which defined like this is Pn sum over phi and I to the power 4. So phi is a wave function, n is a eigenstates which you consider. So you can consider different eigenmodes with increasing energy. And then I is kind of what is the participation of the amplitude of this wave function on a particular site. And this quantity is used quite a lot in this localization physics. And basically it's because this quantity P of n has very different behavior if you have delocalized mode or you have a localized mode. If you have a delocalized mode, that means that your wave function is spread all over the system. And roughly speaking, that means that all sites participate, and therefore it should be very small, and moreover it should be very much depending on the system size. So basically each state will contribute as 1 over n, and if you're going from the different system size, you'll see that this quantity should change. However, if you have a localized mode, in this case, this mode will have a wave function. Those amplitude will be spread only on the small region. And therefore, roughly speaking, you can hope that only a small number of sites contribute. And you can say that that's order of 1. Okay, so it should be a bigger number. It does not need to be exactly 1. The wave function, the particle will not be localized on this particular state, on this particular site, but it will be some small area where you would see increase in the inverse participation range. And here what you see is that at low energies, if you have a bond disorder, if you are in the zero flux sector, you don't have any localization. So basically all these red dots, so IPR computed is shown shown by these red dots. So you see that at very low energy states, you have no localization. All states are delocalized. However, what you see that if you and that remains true if you have also thermal fluxes. So if you have bond disorder, so this plot L, if you have a bond disorder, a strong bond disorder, so here also 25% of the bonds are affected by this disorder. And the binary disorder means that here you have just 2 values of the bonds, and the difference which we consider, I didn't write here, but the difference which we consider is 1 and 1.8, okay? So then what you see that you do have, in the random phase, you do have some increase number of low energy states, you have some pileup of the states at very, very low energies, but these states are not localized, they remain delocalized. However, what we see in all this picture that at the high energy age of the bandwidth, we have the increase in the IPR numbers. And this, we can, actually, we have this increase, but we can also look at these high energy states. We can plot the amplitude of these high energy modes in two particular cases. So here we compare when we are doping weak bonds and when we are doping strong bonds. So normal bonds are 1, and here the 10% of bonds has coupling 2, and on the left, the 10% of bonds have coupling half, okay? So, and what you can see that these high energy states behave very differently in this case. So when the majority of bonds are strong bonds, then you don't see any increase in IPR at the band age. And once again, you see that these modes remain pretty delocalized. So it's spread over a big portion of the system. And this happens for the following reason, because the overlap of the high energy mode with high energy, it happens mostly with the modes with the same energy or close energy. And here on the left, this is the majority of the bonds. So therefore, this delocalization is happening very naturally. However, when the majority of bonds are weak bonds, then the bonds which has very high energy around J prime equal 2, they have very few neighbors, or the probability that their neighbors has smaller couplings are significantly strong. And therefore, these modes are significantly more localized. Basically, they are staying in the area where you have stronger bonds, but they are confined by the weak bonds. And in fact, this phenomenon is known as Lifshitz tails. And this Lifshitz tails is very relevant to the first Anderson paper when he was considering the disorder effect for the free fermions hopping on the lattice. So it's very, very much the same phenomenon. So basically what we see here, this increase in the localization for high energy states is nothing else as a Lifshitz tails. Okay. So that's about the bond disorder. Now let me discuss the site disorder. So, and site disorder, once again, can come from different reasons. So we can have pure vacancy. In that case, the atom are just simply taking out. Or we can have a quasi-vacancies where we can have some local we can have some local couplings which become weak for some reason. And it's kind of very strong but very rare bond randomness. And what we are going to discuss is these two cases. So the true vacancy corresponds with this coupling of the sites to the neighboring sites with J prime equal to 0. And the quasi-vacancy when this J prime is small, but still non-zero. And what we will see that we'll have still this quasi-localized mode, which will be around the vacancies. And we'll also have the effect of the flux binding. And here for the moment, I consider time reversal symmetric case when kappa is equal to 0. How I'm doing with time, so just.
Well, there's about 10 minutes left.
Okay, thank you. So, so what I want to say is the following, is that when we have this, as I said, so we can check two things. So one is that if we have these vacancies that flux are bound to the position of the vacancy. And that was actually first shown by the paper of Willems et al. In 2010, where they did analytical calculation for strong coupling regime when the couplings were very different. And in the isotropic mode, when you introduce, in the isotropic model, when you introduce vacancies, you can actually show these numerically. And basically what you need to compute, you just put, you do the estimate, you put the two vacancy in the system, and then you compute the energy of the system where you have no flux bound to these vacancies, and when you have flux bound to the vacancies. And basically what you can show is that when you bring these two vacancies quite far from each other, then the energy of the system lowers when you attach flux to the vacancies, and this flux binding energy is around 0.02 of J. And we can also show, so there are two plots here, is one that this is basically system size independent, so you really consider different system sizes, and this flux binding energy is kind of the interpolated value. But second, you see that this flux binding effect survives for small j prime, so it's also survived for quasi-vacancies when this connection of the intermediate size to the neighboring j prime is smaller than this 0.05. So it's numerical estimates where we can talk about this flux binding effect. Okay, so in this case, once again, this is how we construct different bound flux sectors. So what we do, we always consider the compensated case when we have equal number of A and B vacancies. And each time we create, we put these two vacancies together, we create with this changing of U, the attached flux to them. And then we just bring these vacancies far apart, and the fluxes move together with the vacancies. That's how we construct various flux configurations. So what we see here, so here what we compare is the pure model again, with the situation when we have 2% of the vacancies, and we consider that the flux is attached to each of the vacancies. And here we see that there is some pileup of the low energy states, and that these low energy states basically they go, the states are present almost to zero energy. And here in this inset, we show that this divergence in the density of states is e to the -1/2. And actually, it's very important that you can achieve this divergence for explaining the experiment about the hydrogen intercalated lithium iridate. I'll probably only will have time to say a few words about this. So now, once again, the same analysis for the vacancies, what we did before for the bond randomness. So here what we do, we consider the density of states and inverse participation ratio for system with different concentration of vacancies. So this is 2%, this is 5%, and these two cases corresponds to the pure vacancies. And plot C corresponds to the 5% of the vacancies with very small coupling, so it's a quasi-vacancy case. So what do we see here? So once again, we see here that this latest case corresponds to the largest pile up of the low energy states. And we also see that when we look to inverse participation ratio, that we have a strong localization of these low energy states. And we again have some Lifshitz tails on the top. So here again, we plot the amplitude of the real space wave function. And we see that these low energy states, so here we take one of these low energy states and plot the configuration for that, that they're quasi-localized. So basically, we see some localization, but it's quite weak. And this amplitude is decay as 1/r alpha when alpha is smaller than 1 with the distance. So we can only talk about quasi-localization. So, and we also see some Lifshitz tails, which one can explain in a very similar ways I discussed before. So here, once again, what we see is just to compare how, what is the competition between the site disorder effect and the thermal effect. So we see that actually, while the pileup of the states remains in the low energy state when we have thermal flux, when we have a random flux, nevertheless, the localization, I mean, it is present there. You need to see that this IPR has a very different numbers here and there. Okay, so you need to compare the absolute. So also there's some quasi-localization present in the random flux case. So what I want to discuss now is how we can use the dependence of inverse participation ratio on the system size. Okay, so this once again related to the behavior of this inverse participation ratio for the localized mode. So we expect that it will have a strong system size dependence. Okay, so what we plot here, so the first two rows correspond to the vacancies, and the C and D corresponds to the binary disorder, the strong disorder. And what we want to compare is how the distribution of inverse participation ratio is changing with the system size. And we also compare how the overall system behaves when we consider all values of IPR. So with IPR computed only for very low energy states, for the states inside the pileup, so this is with the energy smaller than 0.05. So we consider two system size with L equal 20 and L equal 40, and we compute, so it's a log-log plot, and basically what we expect, since on the horizontal axis we plot log 10 of IPR minus log 10 of IPR, so when the system size is increasing, we expect that the distribution will shift to the right by log 10 of 4, so by 0.6. So this we expect in the case when we have totally delocalized mode. So now once again we can look panel by panel. So for example, we can consider first kappa equal to 0, so it's time reversal symmetric case. And we see that if we consider the distance between the peak in the distributions of IPR, then when we plot all the states, we see that the majority of states which contributes to this IPR, they are delocalized. 0.575 is not so far from 0.602. However, if for the same case, we only take into account the states with very low energy, we see that the distance of this peak is significantly smaller. It's 0.375, which tell us that these states with the low energy, they're significantly more localized than the states in the bulk. Moreover, when we switch on the time reversal symmetry breaking term kappa, once again, we see that for the majority of the states, this shift even increase, and that tell us that since we have additional second neighbor hopping for Majorana fermions, there is additional source of delocalization, and the bulk of the states, the majority of the states remain delocalized. However, when we look to the low energy states, they are now inside the gap. They are now inside the gap introduced by this time reversal symmetry breaking term, and they see that their localization becomes significantly stronger. They are not still fully localized, but once again, they are significantly more localized. So it's a very strong effect. When we have bond disorder, this is this last lower two rows, what we see is at the beginning, when we consider the shift between the system size, it's actually smaller than this, but you need to look to overall numbers. And once again, these states are probably less localized, but they're still quite localized. And when we consider the low temperature states, once again, they are a bit more localized, but they are more delocalized than in the case of the vacancies. But what is interesting that the effect of time reversal symmetry breaking term is actually opposite. So what we have is this low energy states. So if we only look to this panel, in the presence of time reversal symmetry breaking terms become more delocalized. So really these two behaviors are opposite when we introduce the bond disorder and when we introduce the site disorder in the form of the vacancies. Okay, so basically what I wanted to show there is that this behavior is very diverse and really depends on the type of disorder. And then since we are talking about the states and we are talking about the level of their delocalization, so the localization is actually also the question about the transport properties of the system. And once again, the study of localization, Anderson localization in the electronic system is very much related to the properties in the conductivity and the resistivity. So a lot of work was done in this direction. So here, since we are dealing with insulator, so we only can compute the thermal conductivity. And for the moment, we focus only to the longitudinal thermal conductivity, which is not related. So that's why in principle, we can consider kappa equal to 0. We can discuss, I will not have time to discuss other effects. But in any case, here we can assume first that the thermal conductivity of the system will be only from the contribution of Majorana fermions, and that means that the phonon contribution can be effectively subtracted. If this is the case, we can compute thermal conductivity using the Kubo formula. So this basically the result that it's proportional to the current, it's energy current correlator. And we follow, so this was done already by a group of Matomi and Wolfram Brennick for the Kitaev model. And basically in this case, we can write the energy current in terms of the Majorana fermions. And this is the explicit expression. And from this expression, you see that first of all, the terms which contributes to the heat current or energy current, in this case, it's the same thing, is the Majorana fermions hopping on the second neighbor. And also these U variables present here tell us that the fluxes will play a role in the evaluating of thermal conductivity. Then we can divide the thermal conductivity, this is a standard approach, in two parts. One is Drude part, which is non-dissipative or ballistic contribution. And then we can have this part which is dissipative as a function of omega and t. So this is kind of omega equal to 0 contribution, when omega is going to 0. And we can compute this, where is once again following the approach from Matomi paper. And we can see that the states which contribute to the Drude current, they are diagonal states. And what contribute diagonal terms, and once again, this is the matrix elements, and they are very important, this matrix element Jx, K, and prime. So these are matrix elements of the current operator. And that the contribution to non-zero frequency and at finite temperature in the dissipative part is mainly coming from the off-diagonal terms. And once again, here we follow the approach from Matomi's group, and we do our calculation numerically on the cluster. So basically, we have a super lattice. So we have a lattice where we compute the spectrum for Majorana fermions, from which we form the super lattice. So the calculations here are shown when the unit cell has dimension L equal 20, so it's 2L squared sites in the unit cell. And then we have 100 super lattice in order to compute the thermal characteristic. So, okay, so this is the Drude weight. And what we can see immediately from here is, so here what we show is for the L equal 20, and this is 0 flux and no vacancies. So this blue line here shows the Drude weight for the pure model in the 0 flux sector. So basically, in this case, the energy current operator commutes with the Hamiltonian, and therefore there are no off-diagonal elements, and therefore all the weight is going into the Drude weight. So therefore the Drude weight is finite. And then we can show that actually, so when we introduce the vacancy in the bound flux sector, so this is this kind of different system sizes shown here. we see that, first of all, the presence of very weak disorder in terms of vacancies. So if you compare this magenta line for L equal 20 with the blue line, which is for L equal 20, you see that the suppression is very strong. So basically, the finite temperature Drude weight diminishes very quickly. And also here, what we plot is the maximum of this Drude peak as a function of the system size. And we can see that in the finite system that will still be there, but in the when we are going to bigger and bigger system, then Drude weight diminishes and it should completely vanish in the thermodynamic limit. So it can be observed only in on the finite size system, but the system size can be rather large. Okay, so now basically this just to explain how we analyze this dissipative part of the thermal conductivity. And for that, since we want to study the temperature dependence of this, we need to consider the contribution not only from disorder, but also from the thermal fluxes. So the way how we account for the thermal fluxes is the following. So this plot is from the Monte Carlo result, and we see what is the flux density, characteristic flux density for each temperature. So now for each temperature in all the remaining plots, we consider various flux configuration, but with this fixed flux density, which we obtain from Monte Carlo simulation. Okay, so here, what we plot is the kappa XX for the pure model where only thermal flux disorder is taken into account. And what you can see, once again, from blue to red, the temperature is increasing. So what you can see that at very low temperature, you basically have no contribution. And this is because at very low temperature, the system is mostly in the zero flux sector, and therefore the current operator still commutes with Hamiltonian, so it's a conserved quantity. And therefore, the contribution to this non-zero frequency is very, very small. So when the temperature is increasing and basically you have some flux appearing there, so your current operator is not anymore commuting with the Hamiltonian, what you see, and this growth happening very, very quickly, you see the growth in the thermal conductivity, and you have a formation of the broad peak around maybe energy around 3 or 2.5. Okay, so you have this peak in the thermal conductivity. And then you see that with the temperature, this peak is shifting to the low temperature. And all these reddish curves, or even already yellow curve, they all dominated by the contribution from the random flux background. And therefore you see that this both the peak is shifting for low and lower frequencies, but also the size of the peak is decreasing. So now, okay, so basically here you can take this formula and you can try to look to this formula at very low temperature and at a very high temperature, and you can see what contributes. So the most, what is the contribution of the matrix element, and what is the contribution of the Fermi distribution factors. And basically what you can show that if you look to a very large temperature range, to all the temperatures, you see that at high temperatures, when you have mostly random flux background, your peak dependence of temperature is basically, it's proportional to T cube. So what is plotted here is the maximum value of cube multiplied by T cube as a function of T over J. So, and you see that in all these cases, both the pure model and the vacancies, the behavior is, this curve is almost linear. So that means that the maximum more or less scales as T cube. And basically this thermal factors plays the dominant role. But if you look to the very low temperature, then here you can see some difference. You see the deviation from this temperature behavior of the peak, and you can start seeing some subtle difference between different disorder models. But let me show you this plot, which is probably more characteristics. Once again, what we show here is the behavior of the thermal conductivity for 5% of the vacancies, and for the binary disorder, so the strong disorder versus weak disorder. And we see that behavior is very different. One thing which is different from the pure case is that already at the lowest temperature, you have non-zero and quite large contribution into the omega. But also you see that for the vacancy, that is about the structure of these pileup states in the density of states for the vacancy. When the temperature is increasing, you're kind of using less and less the states inside the pileups, and therefore this kind of structure has this kind of triangle shape. It's decreasing pretty rapidly. And then you can look, so this, what is shown in the inset is a higher temperature, and that is very similar from the pure case. And once again, the main contribution at higher temperature is just from the thermal flux randomness. And for binary disorder, you see much broader distribution. Once again, it reflects the density of states at very low energies. And these two at very low temperatures are different. But once again, if you go to the inset where high temperatures are shown, then you see that the behavior is again similar. So what we can also do, we can extrapolate these curves. So this is for the pure Kitaev model, but we can do the same for each of the disorder case. And we can obtain what is kappa XX when omega is going to 0. What is the coefficient? And then we can plot this coefficient kappa XX as a function of temperature. So what we get from here is that indeed that the presence of disorder suppress thermal conductivity pretty strongly, and especially the binary disorder will suppress it quite quickly. Okay, so, and I think that would be the conclusion for my talk. So the conclusion for this part is that basically the presence of site and bond disorder, first of all, they preserve most of the quantum spin liquid behavior. But what it does, and that we can say that when we look to the density of states, we have only small changes at very low energy behavior and at very high energy behavior. But overall, the flux gap, unless it's very strong binary disorder for bond disorder, will be finite, and that's why that will preserve the quantum spin liquid behavior. And then, because we have these Majorana fermions which are non-interacting, and they are non-interacting even in the presence of disorder, then this Kitaev quantum spin liquid is an interesting playground for one-body understand localization. And once again, that is very much related to the concept of spin fractionalization in this model. Okay, so basically what we say that localization is observed in the vacancy-induced pileup of the low energy states. We also observe Lifshitz tails at high energy of bond disorder. And we said that even without extrinsic disorder, the thermally proliferated fluxes in the pure model suppress the ballistic thermal transfer. I have no time to talk about second part. It's about hydrogen intercalated lithium iridate. But let me show just one plot, which will show that the ideas which I already discussed actually can account for the observation of various properties. So these are all the key observations in this hydrogen intercalated lithium iridate. And it was a lot of theory, and I will skip all this plot and all this discussion. What I want to show that here is the plot for 2% of the vacancies which we study. And basically we show that when kappa is this time reversal symmetry breaking term, which mimics the effect of magnetic field, is increasing, then the ground state is going from the bound flux sector to the free flux sector. And this is the behavior of the specific heat based on the density of states, which we compute for all these different kappas. And here what we see first, that we see the pileup of the of the low energy states in this case, and we see this increase of the specific heat, of the fermionic specific heat, which was shown in the paper by in the group of Takagi. This is this B equals 0, the blue curve. You see this upturn in the specific heat curve. And then you see that this magnetic field, the same as in the experiment, suppresses this pileup. So that means that this amount of low energy states which participate in this specific heat is decreasing, and the scaling behavior which was obtained in this experimental paper can also be almost quantitatively shown in this case. And once again, what one needs to look for this is the behavior of the in-gap modes in the zero flux sector and in the bound flux sector. So at the beginning, when we have the ground state is when the vacancy is, so the fluxes are bound to the vacancy, we always have some amount of low energy states, and they contribute, these states near the middle, they contribute in the upturn of the specific heat. But once kappa is increasing and we are going to the zero flux sector, then these states are depopulated, and basically we have this gap between the states, and therefore this upturn is suppressed as observed in the experiment. And basically, once again, this is the conclusion for part 2, for which I didn't have time. And the conclusion is that even the Kitaev spin liquid can semi-quantitatively explain the results in this hydrogen intercalated iridate. And once again, it's very much depends on the behavior of the low energy state. But of course, if we want to make a truly quantitative comparison, then we need to remember that this compound has all other interactions. It's not a pure Kitaev interaction, but it has also Heisenberg interaction and gamma interaction. So, and we need to check how disorder affects this term, and maybe less exact calculation can still be performed. And with that, thank you very much for your attention, and sorry for taking longer time.
Okay, thank you very much, Natalia. So, are there any questions? Let me start perhaps with a simple one then, and sort of break the ice. So, these super lattice that you introduce is just to smooth out the delta functions that you get in finite system. Is that right? I mean, you said L equals 20 and N equals 100 super lattice.
Yes, so L equal 20 is the system, and then you repeat the same system. So you compute your the spectrum with L equal 20, and then in order to perform this calculation, the momentum space is included in this super lattice.
So that sort of broadens the peaks in some way, or puts more delta functions in.
Sure, sure. But it's also kind of important to, I mean, if you want to have some sort of the gradient of the temperature, so you don't want to have this kind of distinct states.
Yes. And then another quick question is, so how do you compare these effects with the effect of non-Kitaev terms, you know, in the real materials like Heisenberg and so on? Is there a distinct way to say that it's coming from disorder instead of from these other
I mean, we didn't do this, okay? So this is basically all our calculation is based on the exact solution of the Kitaev model. The only thing what we allow the translational symmetry breaking by introducing different bonds and basically solving all the problem on the finite size system in the real space. That's the only thing what we include. So I believe if we want to take other terms, first thing we need to do is some sort of mean field decoupling. And this can be done, but this is non-trivial task. And once again, I hope we'll do it, but...
no, but I think people have done non-Kitaev terms. So, I mean, you can just look at their solution and compare it with yours and see.
I mean, we also consider other terms. But the question is, how you compute the quantities, I mean, how you compute the spectrum. So once you add all these J and gamma term, your flux degrees of freedom becomes, they're not static anymore. So this idea that you can do the calculation in different flux sectors is not valid anymore, because these sectors are not anymore orthogonal to each other.
Mm-hmm.
Therefore, you can start doing it perturbatively. You just assume that these couplings are very small and the flux gap is not closed yet. And basically then you try to do it in the mean field sense. This can be done, and in principle we plan to do it. Then you do the self-consistent system of equation and so on. But the problem is that it's easy to do the self-consistent mean field calculation when you can do everything in the momentum space. When you need to generalize the same thing with the disorder and do all the self-consistent calculation in the real space, at least we didn't succeed yet to get a good convergence. Perhaps there are some tricks to do it, which we still need to learn, but I mean, this is not done, at least not done by us. I will be happy to see how people are treating these problems.
Okay, thank you very much. So Bruce, you have a question.
Yeah, actually, I had a couple of questions which are sort of experimentally focused, which is probably unfair.
I can actually put back the slides. It's just because I could not see anybody, so I stopped sharing. But if you have questions for the slides, I can put it back.
Well, I was gonna. So I was kind of expecting that at some point there would be a, there might be a discussion of intentionally doping some of the Kitaev materials to put. It's very hard to make pristine materials, but it's easy to make dirty materials, and so you can always put in disorder, at least certain types of disorder, and so you might be able to systematically study more and more disorder. I just wondered if that had been done.
There are some works where ruthenium chloride was doped by, I think by iridium actually. So, and maybe by some other elements, but I don't know, maybe Hayung knows this better, but I don't think that they succeed some very systematic doping and really try to see that you are still in the spin liquid. I mean, and the doping like 2% or very small percentage of, it seems to me that what I saw was some papers with a rather big doping. So when there are already good samples, but then this physics is already not, not applicable for that.
Yeah, I mean, it kind of makes sense because, a lot of the effort goes into making things as pristine as possible.
I didn't see any experimental work where the doping would be on the very low level. And in that case, we can still consider that these vacancies which we introduce, they're at least weakly interacting. Basically, we still compute it in the approach where it's a very weak disorder, very small number of the small density of vacancies. And therefore, we can still associate the sites with these vacancies in a clear way.
Yeah, and a somewhat related question, especially the example that you gave at the end, the hydrogen-3 lithium iridate. The hydrogen and the lithium are very light, and so it could be that even in a nominally pure material, you've got very large 0-point fluctuations at low temperature. So the phonons themselves may be able to generate disorder because the fluctuations around the equilibrium positions would be very large. And I was just wondering if there was if anybody had considered that, and for example, if you substituted deuterium for hydrogen, you could lessen that effect.
Yes, exactly. Yeah. So basically, as far as I know, so the results which were published, I know that there's still work going on, is that because hydrogen is very light, so its position fluctuates quite a lot. Okay? And then basically you can associate it with some, and at the beginning we were trying to address this question with the bond disorder, thinking as some other people that this position of hydrogen will modify J's quite a lot. But the problem in our first calculation, and once again, that's now very clear from this density of states which I presented, is that in the bond disorder, you need to have a random flux configuration in order to see this pileup of low energy states. And basically, that would mean this completely random flux configuration will mean that the flux gap is significantly diminished or it's zero. But then it's a question if the quantum liquid behavior is actually preserved or not. As far as I know, with the deuterium, they really see two position of deuterium, so it's kind of either close or far, and therefore there is a hope that kind of disorder is more control. And I saw recently there are some studies which compare these two cases. So yes, so that was done with deuterium. And the role of phonons, I think it's also the combination of phonons and disorder is very interesting, but once again, it's remained to be understood.
Okay, thank you.
So, Jan?
Yeah, actually, I have two questions, but apparently Bruce has already asked one. It's about the phonon that I had a similar, but I can probably ask a slightly different perspective. So yes, hydrogen and deuteriums are light, so you will have phonons. But in addition to that, when you're thinking about the thermal conductivity, it is the phonon that will couple, and it probably has some impact on the thermal conductivity and dissipations and so on. So that's one question. I wonder if you have thought about it and how.
I do think that, especially when, and one of the reasons why I show only kappa equal to 0 is to kind of better justify separation, that there are no cross terms, and to some extent, I assume that we can compute the phonon contribution and then subtract it from the total thermal conductivity and look only to the contribution from the electronic carriers. But I know myself that the phonon, there is a strong magnetic elastic coupling between phonons and these itinerant Majorana fermions, and there will be some cross term which would also modify the spectrum. There will be the decay of the phonons in the Majorana fermions, and since in the presence of disorder you have a pileup of the low energy state, this decay will be enhanced. That's what we are going to analyze, but this is not done yet. It's a combination of to analyze what would be the phonon decay in the presence of various type of disorder. This can be done, but once again, not yet.
And another question is about the your Wison gap, the flux gap that you want to think about. Because if you want to add another interactions and test of perturbations, I was just thinking that you might want to have a term that enhance your flux gap. In that sense, maybe a gamma prime term, when they have a magnetic field and gamma prime with a right sign, you can actually enhance your flux gap. And that situations, probably those random flux, and then your state might survive still better. So
Okay.
I thought
that would be good, because we all know that when you add like other interaction, both gamma and J, then the gap is decreasing.
Right.
And then all these kind of justification become, these thermal flux sectors reduces to either zero flux or to random flux, and all this dependence on this different flux density becomes irrelevant. But if you are saying, this I didn't know, but if you are saying that gamma prime is increasing the flux, then it's probably the best case to consider, because
so
that
I thought that,
stability.
I think you need I think there is a linear term that couples with a gamma prime with a magnetic field. I think it has to be antiferro or something, antiferro gamma prime, because ferro gamma.
I would be happy to discuss it.
So we can discuss it, but I think that's a way that you can enhance your.
I think that would be good, because the worry always is that if you take other interactions and you compute in the mean field decoupling, you compute how the flux gap depends on this interaction, it's always going down. It's only the question, is it going down very fast or slowly? If it's going up, it's probably the game changer. So that would be
small one, it will go up.
then that's good. But I didn't know about this, so okay.
Bruce, you had another question?
No, I just wasn't able to lower my hand, actually.
There it is. Go.
Okay.
So any other question? Okay, well, if not, let's thank Natalia for this nice talk.
Thank you very much. And once again, sorry for taking longer.
And we'll see you in 2 weeks then for the next, no, 2 weeks is March meeting. So 3 weeks from now, right? Okay. See you then. Thank you again. Thank you. Bye-bye.
Bye-bye.